switch to the next talk by Professor Samir Shende. He presented our case yesterday. So today we'll be going more into the tau performance system. So Professor Shende is the director of the Performance Research Lab at the University of Oregon and the president and director of ParaTools. He serves as the technical lead of the E4S, ParaTool Pro for E4S, tau performance system, and program database toolkit projects. His research interest includes scientific software stacks, performance instrumentation, compiler optimizations, measurement and analysis tools for HPC. He received his BTech in electrical engineering from IIT Bombay in 1991 and his MS and PhD in computer and information science from the University of Oregon. So let's give again welcome back, Samir.
Thank you, DK. Thank you for inviting me. And today I want to describe the tau performance system in greater detail. I know some of you saw it yesterday. And I would like to first thank the MVAPitch team for their support and collaboration, and my colleagues in the tau performance system team. The key motivation is that with growing hardware complexity, it's getting harder and harder to accurately measure the performance of our HPC and AI/ML workloads. And our goal here in the tau performance system is to deliver a scalable, portable performance evaluation toolkit for both HPC as well as AI/ML workloads. And it's a comprehensive profiling and tracing toolkit with support for instrumentation, measurement, and analysis tools. It integrates with your application frameworks very easily. It's open source, BSc style licensed, and it uses performance and control variables to interface with MVAPitch MPI runtime. I'll describe that in greater detail. This is our web page. It supports a number of different runtimes, including MPI, CUDA, ROCm, DPC++, SYCL with level 0, OpenCL. If you're using OpenMP with target offload directives, you can use tau. You can use it with OpenSHMEM or Nickel or RICL. All of those libraries have hooks that translate into tau timer calls, which will show you the detailed profiles and traces that you can get. We also support PAPI liquid for hardware performance counter information, and tau can itself access the hardware performance counters that are present on GPUs. And I mean GPUs from NVIDIA, AMD, as well as Intel. And we can also access the the timer libraries that are already integrated in many libraries such as PETC or GPTL or FIPROF or CAM timers libraries, also COCOS, MPI, and then you can enable other features of tau such as event-based sampling. The key thing to take away from this is that there is a single tool called tau exec. You can use tau exec to launch your application, and then you will be able to generate profile files, traces. And then you can use tau's paraprof, pprof tools or Vampire, perfetto.dev to look at the trace files. And in case you are wondering, what can tau show me? It can show you how much time is spent in different code regions, whether these code regions are in function level code regions or at the statement level on the CPU as well as on the GPU. You can see the time spent in kernels, the time spent in OpenMP regions, even the time spent in assembly language code that's running on the GPU at the statement level. It can do sampling on both CPU as well as GPU. It can access hardware performance counters on both the CPU as well as GPU. It can look at the time spent in the application, which is wasted waiting at a barrier call, like MPI barrier, within the collective operations. As you scale up your codes, you're going to use a lot of collective operations. And if there is a load imbalance in your application, you will spend a lot of time in the MPI barrier calls that you did not insert in your code at all. But these calls were called implicitly by the MPI collective operations, and it can pinpoint where exactly those calls took place and how much time was spent wasted over there. It can show you the memory usage of the code, even the memory footprint, the high water mark of the virtual memory used. It can show you energy usage in your application, peak power, I/O characteristics, even how the application scales. Here is a quick cheat sheet on using Tau. If you want to just use an MPI program and generate profile files, you can launch it with Tau exec with a -EBS, event-based sampling. It will show you the time spent in different code regions. If you're using CUDA in your application, then you can use the -CUPT flag for CUDA profiling tools interface. If you're using ROCm, you can use the -ROCm. Or for Intel GPUs, if you're using level 0, then or DPC++ SYCL, you can use the -L0 flag. If you have a Python code, all you need to do is replace Python with Tau Python. If you have a Julia code, you can use Tau Julia. And you can then use pprof, paraprof. If you're using perfecto.dev, then you can generate trace files and load them in Perfetto. Here is the Tau architecture. There are three main components: instrumentation or adding hooks to your code, measurement, generating profiles, traces, and analysis, where you can visualize the profile data, visualize the trace files. Here are the three main parts of it. Instrumentation, we support a large set of languages and runtimes and analysis tools. We also have a database called TauDB, where you can store the data and then access it using tools such as Paraprof and Perf Explorer. And to add hooks to your code, it can be done through a preprocessor, where you can parse the source code using a toolkit called the Program Database Toolkit, or PDT, or you can use the compiler for compiler-based instrumentation. And this is also used extensively in Julia for LLVM plugin with rewriting the intermediate representation. And the simplest way is to just use the Tau exec tool, which preloads the Tau's dynamic shared object, or DSO, while running your program, and then generates the data. And it supports a number of different runtimes. At the MPI level, we support not just the PMPI interface for entry-exit into MPI calls, but also the MPI-T tools interface using the performance and control variables. And MPI-T acts like a bridge between MVAPIC and Tau. We also support the collective sync time, the time in an implicit barrier that I described. pthread instrumentation, OpenMP tools interface for OMPT target offload, Intel level 0 to capture the time spent in kernels, as well as the level 0 runtime calls, OpenACC instrumentation, OpenCL, CUDA, ROCm, Cocos, Python, Julia. And the best part is you can mix and match these modules. You can say, if I'm having an application that uses MPI with CUDA, then I can use, say, PMPI with the CUPT interface. You can launch the application with Tau exec and then enable other components or other parts of Tau, such as the communication matrix generation component or the generation of OTF2 or event-based sampling. This is how it looks. If you say Tau exec a.out, then it will generate the MPI data like this. But if you say Tau exec with ROCm, then it will show you the time spent in all the kernels on the AMD GPU. If you say ROCm_PC, then it does PC sampling on the GPU, and you'll be able to see which instructions on the GPU were taking time. The same with CUDA, with CUPT or CUPT PC, and Intel GPUs with L0 and L0_PC for sampling on the GPU. If you want to sample on the CPU, you use EBS or event-based sampling, and you can even specify Tau metrics to be environment variables, which include GPU counters And you can set this with ROCm or L0 or CUPT for GPU metrics to access GPU counters. And of course, you have I/O and memory debugging capabilities, and even OpenMP tools interface with the -OMPT. You may notice this -T, and that's referring to some tags in a configuration of tau. These are the configurations. If I look at the modules on Aurora at Argonne National Labs, I'll see that tau is installed over here. And you can see all of these modules for level 0 and Intel compilers. And you can see ITT notify, GPTL. And you can then take these tags and use them with the -T option. In their case, you use the GPU tile compact.sh before the tau exec. You can also pack the profiles into a PPK file, bring those over to your desktop and launch Paraprof with it. And here is the usage, an example of how you would use it on Aurora. There's a workshop tarball as well. And this is at Oak Ridge National Labs, where we have the same kind of a UMS user managed software module. You saw that MVAPITch is installed with the UMS 0038. We have 002, and you can just say module load UMS 002 tau, and then tau will be in your path. And it would be very nice if we can have such UMS modules on other systems as well, where you can then say tau exec ROCm or ROCm PC. You can set tau metrics to be something like ROCm SQ waves. You can run this ROCprof v3-L for a complete list of the GPU counters that you can set, and then launch tau exec, and then pack it and launch Paraprof. So this is the typical workflow. If you are using the cloud-based environment like we were using yesterday, like on Microsoft Azure, you can just use tau exec in front of an application name and then launch it. This is with a PETC example. And then you can see the profile files and launch Paraprof, and then look at, say, the thread statistics table. Here is a pprof output that shows you how the PETC timers are mapped into the tau calls. So you can see in detail all the timer calls from PETC. And if you turn on the tracing and set Perfetto as the trace format, then you can generate Perfetto traces that can be loaded, which show you along a timeline what happens at the GPU level in the CUDA kernels, or on the in this flame graph, which shows you the calling context for the application. And this is along a timeline display. And you can then click on a particular function. This is on Vista at TAC. We have AWP ODC, and the traces include detailed information on the GPU, where I can then look at the kernel name like this, and then see where that kernel is executing along a timeline display on using Perfetto. Here is an example of the Paraprof using AWP ODC. So you can see on each of those MPI ranks or on the actual threads on the GPU, you can see the name of the kernel over here and how much time is spent in kernel seconds on each of those GPUs on Vista. And here is the MPI collective sync, the time wasted in the MPI barrier called from within a collective operation. And you can then see exactly where that collective operations call takes place, in this case in mesh.c at line number 588, where you can see the time wasted in barrier at that point. And you can then compare the performance of libraries like Hefty using MVAPITch's data compression features. Data compression allows you to just reduce the volume of data that's being sent. And then you can see over here that you get a significant speed up on a particular thread comparing two different experiments. So you can see the total time and it's about 20% less in the overall time when you run it with compression. And you can see the immediate benefit of using this MPI all-to-all in this particular case. This is the sweep C2C test case on 32 MPI ranks, again running on Vista at TAC. And thank you very much, Dan, for your help and access. And this is the MPIT interface that allows Tau to communicate with MVAPage and exchange information, gather detailed information using MVAPage stored performance variables, and control at runtime the performance of MVAPage using the MPIT CVARs. And you have this is the model for Tau, where you can see how the enter-exit events take place. And then you also have a plugin architecture. Now, if you create your own tool, you can create it as a plugin of Tau and load it in an uninstrumented, unmodified binary. Tau will then take that plugin, instantiate it, and then you can get the events that Tau sees and then make those measurements. You can register a plugin and then register these callback routines, which will be triggered when Tau encounters those events, and it will pass it on to your plugin. And then you can define your trigger states. And here is the runtime control of that plugin to access the internal data structures. And this is how it looks, where entry and exit functions are used. And these are the performance variables that are exposed by the MVAPage runtime to Tau. And you can see the names of these variables. And these are the control variables that are exposed by MVAPage. And you can then set these environment variables, like turn on tracking of MPIT performance variables, or set the control variable list. And then you can set their values and just launch the application with Tau exec, and then it will run that experiment. And then you can see here the time spent in a particular example here. This is E3SM. And here I can pinpoint the time wasted in MPI collective sync. This is on the Aurora system, and I can see that the time wasted in MPI barrier was 428 seconds. It came from MPI bcast, and you can see exactly where that happens. And all of these timers, you see, they are coming from the E3SM calling the GPTL timing library, which internally ends up calling Tau as we implement the same interface. We also see all the events at the MPI level, all the events at the COCOS level. You can see the names of the functions in COCOS like this: COCOS parallel for and MPI calls, and the time spent in, say, MPI all reduce when it was stuck in the barrier. And this is something very insightful. If I see that 428 seconds were wasted in this collective sync, I can look at this thread call path relations window, and it will show me that MPI bcast was the culprit. It accounted for 365 seconds of that wasted time. And then you can look at where exactly that was called. And all these timer names are from the GPTL library. So when you see L underscore, that means the landmass. If you see the PIO, that's the IO library with the right DRA calls. If you see A underscore I, that's the atmospheric initialization, and so on. And the CPL is coupling. So you can see the names of those internal timers with Tau that can give you greater insight into what the application developer intended for that code region. And then you can see the difference over here in the collective sync time in Hefty, and compare that with compression versus without compression. And you can see again a good 20% time shaved off from the MPI all-to-all application function, and where that happens. And you can also see the names of these functions, and you are able to rewrite the binary using Dynast API, and it will show you all the functions in your application. This is the time wasted in another example. This is NQMCC application, and you can see the time wasted in the MPI barrier. Then you can compare these two nodes and see the time and exactly where that happens. These are the GPU kernels. This is the time wasted in MPI. So it pinpoints exactly where your application is spending its time. And then it can show you along a timeline display where those kernels take place. Now we can also rewrite a binary. Yes, that's right. You can read an unmodified binary, add hooks to entry and exit functions, and rewrite it. You can also rewrite libraries where you could say, I don't want to touch my application. Just take this HDF5 library, rewrite it so that I have entry exit hooks of tau in it, and then run the application using tau exec, using the Dynast API technology from University of Wisconsin and University of Maryland. And you can do this with other runtimes like Rockham over here. And here is an example of using it with HDF5, where I say, here is a filter file, just instrument the functions that start with the uppercase H followed by 5 and any other function name. So I can see the high-level HDF5 functions in my profile file. Or in this case, this is kubectl with Dynast API, and this is running on the AWP ODC code. So all of these function names are coming from AWP ODC, and they are rewritten functions by rewriting the binary. And with this, let me just quickly show you how it's used on a cloud system. This is now using Azure, and it's the same setup that we had yesterday. If you want to see this, just go to adaptiveparallettools.adaptivecomputing.com, click on the workshop tab, session code of 70034, and then you'll get a two-factor authentication email. You can click on the cluster, you can start the remote desktop, and here is the desktop, this time on Azure. So how do I run this? If I say srun-n2-n2 MPI proc name, I am running an application on 2 nodes on Azure. Okay, in the same way, if I say which OSU bench bandwidth, then this is the application. I can run this with srun-n2-n2, and I run this. Now I'm running the OSU bandwidth. It's about close to 21,000 megabytes per second, because we have InfiniBand between the 2 nodes on Azure. So if I wanted to profile this, all I have to do is go here and say tau exec-ebs and run this. And again, with tau, it was 21,000. So it actually improved the performance, right? Here it was 20,777 live demos, and here it's 21,000. So that's like close to 170 gigabits per second that you are getting. And so you can see the overhead of tau is, well, in this case, negative. But here you see the time spent in all the MPI calls, all the functions, and you can even see exactly where the application is spending its time. And it's not just MPI. Let me just remove these profile files. If I have an application, this is with Codium, and this is a Python application. And here is the mstest.py. If I want to run this, I say Python mstest, mstest.py. And it's running this application, and it ran this. Now, you may notice this, that it also, in this case, I have a msickle Python already in this Python instance, where I'm importing this, I'm running this, integrate. Now, if I want to see the performance of this code, instead of saying Python, I say tau underscore Python. That's the only change. And now it will run this code, but it will instrument it, and I'll be able to see all the details of the application functions and all the calling context with Python. So here is the full list of Python routines that were generated by just using tau underscore Python instead of Python. So it can be as easy as that. How does it look like for an HPC application? So if this is PET-C CPU, and I have an application, say ex50.c, here is the system of linear equations that I'm solving in PET-C. I can just say compile.sh, and it will then use all these HDF5 and other OpenBLAST libraries, and I can say sbatch ex50.sbatch to run it. Here is the Slurm output of job 42. It ran it. Here is the ex50.sbatch. If I wanted to just run this myself like this, I could just even say, srun -n2 -n2 -n tasks per node equals 2, and then give this ex50 like that, okay? And it runs this. Now, if I wanted to use tau, all I have to do is go here and say tau exec-ebs and run it like this. The same code, unmodified, I just run paraprof, and I can then see the time spent in all the functions. Inside this, you can even see the time spent in the collective sync and compare the one which has the most time with the one which has the least time by just saying add this thread to the comparison window and then compare these two threads. So you can see that the MPI collective sync time is different. You can see where it is different and compare this. You can even see a 3D graph if you just go to the windows and say 3D visualization, and you can see the 3D plot in tau. But if I want to see what happens during in a timeline, along a timeline, I can just say export tau trace equals 1, export tau trace format equals perfetto, like this, and just rerun this application, remove the profile files, and rerun this with srun like that, and then launch Firefox and go to perfetto.dev like this, and load the trace file and open the UI, open the trace file, and here is home, examples, PET-C with CPU, and here is the tau.perfetto.gz. And once this loads up, I can then see what each of those ranks were doing and look at this in detail like this and see the execution and the time wasted in MPI collective sync. So with this, let me just stop here and see if there are any questions.
Okay, let's first thank Samir. Any questions?
Thank our sponsors.
Yes.
Go ahead.
Do you have any hooks or, so one thing that I do all the time is I trace like system calls. Are those
Yes.
all incorporated in? And then another thing that I started using quite a bit of is like eBPF and BPF trace. Do you have any integrations with that where you can kind of dynamically inject probes into code and then be able to trace those once you've injected them?
So we have done a bit of that inside the kernel with trace points. But as far as syscalls is concerned, yes, tau has a configure flag called -syscall, and tau exec with the -syscall will show you all the system calls. And we also have the -io flag, which is a POSIX IO wrapper if you're just looking at IO calls. So you can see both of those things. Absolutely.
Yeah, because I use that. I use like something like kernel shark, which
Yes.
will get you access to any of the, what's that tracing, ftrace calls.
Yeah.
So do you hook into ftrace as well?
We haven't done ftrace, but with the syscalls, you can get insights into a lot of system calls. So.
Any other questions? Yes, go ahead.
Two questions.
Sure.
One is that you showed a profile where just when you arranged the calls by their time, there was a lot of time on waiting on the barrier synchronization, and you said
Yes.
that it came from broad bcast.
Yes.
On a perfect timeline view, I can probably see that it comes from bcast just by lining up on the
Lining
timeline.
up around that.
But just by looking at how much time was spent on what, how could you tell that it came from?
So we have support for call path profiling in tau. And so if I turned on tau call path equals 1 and say tau call path depth equals say 100, unset the tau trace. Okay. And just rerun this srun like that, then I'll be able to launch paraprof and it will show me the calling context, and I'll be able to see, say, the thread statistics table. And here I see all the call paths like that. And I can then sort it and identify where it's spending its time in main stage, calling PC setup, calling mat-lu vector, and all gather. And this is the time wasted in the barrier when it was called from this calling context. So I have a call path profile that can show me that. I can also look at the call path thread relations window that will show me exactly how much time is spent from which thread. And here is the mat-lu factor. It's getting called from PC setup, and it's internally calling these, and so on. So here is the collective sync, and so on.
Second one.
Yeah.
Sure.
Do you have any plans of something like what an inside compute does, going into one kernel specifically?
Yes.
Do you have any plans of doing something like that?
So we have support for sampling at the GPU level. And if you just turn on like -rockham_PC, it does the PC sampling inside the GPU kernels, and you can see the exact statement that was responsible for the time that was taken. And you can see the assembly language code, the function, and the kernel name. And that's supported for Intel, AMD, and NVIDIA GPUs.
Okay. So I think we have an online question from Benson. Have you looked at distributed memory computing with Julia? How does this compare to other languages and parallel libraries?
So we have support for Julia, a number of different cases where we can do instrumentation of Julia code inside the Julia interpreter by rewriting the kernels and getting the detailed information. We also have a manual API, and I didn't get a chance to talk about the Tau Julia tool here, but it's definitely part of our work. And we have MPI with Julia. We are planning to add support for the distributed.jl. We also have support for other instrumentation hooks. I can provide more information offline.
Okay, so I think with this, let's go for a break. Thanks again to Samir. So we'll take a 20 minutes break. We'll come back by 3:30, and